past few years on explainable, or in fact interpretable AI, with a focus on weather extremes. Okay. And so today's outline, I'm going to present some background about this work. Then I'm going to take a human and a machine view, and I will explain in a second what I mean by that. And finally, I conclude with a question here, whether we can learn through explainable AI. And I will, again, explain what I mean by that. So some background. I like to start with this slide. So here I put three fields. Right? So engineering, weather, and finance. What do they have in common? Or in fact, what they don't have in common? Well, I would like to take perhaps or suggest that maybe engineering and partly weather are knowledge-driven. So, or they are lawful. So we have some mathematical laws or mathematical equations that we can use. For instance, to design the car or understand the flow around that car. So we have mathematical models. And also partly for the weather, as Dale and previous speakers mentioned, we have the Navier-Stokes equation, for example, in the context of weather and climate. What about finance? Well, on the other end of the spectrum, I would call that this is perhaps the far west, so lawless, right? So we don't have mathematical laws that describe the stock market, for example. So if you have one, please share it with me. So this is really a data-driven field. So we use data and we use probabilistic models to perhaps infer some behavior, future behavior, for example, of some of this stuff. This is not a new view. So 1956, Lawrence, in a very nice MIT press, pointed out dynamical versus statistical modeling in the context of weather prediction. And a few years later, in fact, recently, in the past several decades, what people are really trying to do is blend together dynamical with statistical modeling. An example is obviously weather prediction, where we account for uncertainty in initial conditions, for example, with ensembles. So that is a way of accounting for this missing or uncertainty in our understanding of the process. Now, weather, I would suggest, is in somehow the middle between a lawless and a lawful field. So we still have some knowledge gaps in the context of weather, and even more in the context of climate. So the key question here is, can we somehow fill some of these existing knowledge gaps in some ways? So, and what are these some ways I will explain later. We'll take both a human and a machine view. Actually, Dale mentioned this already with a much nicer figure than me, actually. So Richardson, 1922, it was more visual if you want, but I took an extract of this paper, Weather Prediction by a Numerical Process. And Richardson mentioned that several computers were working on different portions of the weather map of our planet to compute the weather. And as it was mentioned, those were human computers, and they were exchanging information with each other. They were exchanging information with neighboring computers, okay? So this is possibly the first conceptualization of a modern supercomputing system where currently we actually run large-scale simulation of the weather. So 100 years later, as Richardson envisioned, we actually are doing that. So these are actually two of the largest ever run simulations of the weather, 1 kilometer resolution, courtesy of Neil Swedey, my former boss at the CNWF and a very good friend. So this larger scale simulation, they produce a huge amount of data, right? So the key question is, can we perhaps leverage this data in some ways to fill some of those knowledge gaps? So I'll take first a human view and then a machine view, or an AI view. So what do I mean by human view? Well, we have this huge amount of data, unified data, right? With human view, I really mean I want to recast myself in something I understand, or we humans understand well, and it was developed over perhaps years or centuries. And I want to recast myself in the context of dynamical system theory, and I want to see this data as a sort of a tractor. So tractor is one of the tools or of the things that you have in dynamical system theory. So we recast ourselves in this framework that we know. So, and we have several tools to study this particular data with these tools. what we are particularly interested in really is in the evolution of this climate attractor in this theory here. So for example, we're interested in looking how this behaves in certain periods of time and so on. And why are we interested in this? Well, it was mentioned earlier that a very important aspect is the space of extreme events. So we know that extreme events are increasing in frequency and intensity due to global warming. And we are effectively interested in understanding how the climate system is evolving and the intersection that this evolution has with climate, with weather extremes, okay? So this is our key task. So to study this evolution, we use analogs, among other things that I don't have time to present today. We use extreme value theory and a bunch of other things, but I will just present this first tool. So what is the goal here? We want to extract weather patterns that best represent this changing climate dynamics, okay? What patterns are we interested in? Disappearing patterns, they were there before, they are no longer there, and appearing patterns or emerging patterns, something that is appearing today, okay? Some dynamical changes in our atmosphere. We can apply this framework to the ERA 5 data, as I mentioned, and we focus on the tropical Indo-Pacific region for various reasons. It is a very important region. It's quite difficult to disentangle, for instance, natural variability from global warming trends, for once. And we focus on the total column water vapor. It is a very important component of the tropical atmosphere, and it has a good intersection with the regional extremes. So we apply these analogs to this region, and what do we get? We uncover some emerging patterns, and this is a very new results that we just submitted. And what are these emerging patterns? Well, first of all, they're clustered in the past 20 to 30 years with some distinct seasonal distribution, and they have a robust trend over the past 80 plus years that seems largely unaffected by natural variability in the region, in particular El Niño Southern Oscillation or ENSO-driven variability, okay? How do they look like spatially? Well, we can look at a few variables, and we can look at this thing here called mean composite anomalies. These are just anomalies in some variables associated to these emerging patterns. So what we see is more water vapor in Southeast Asia, strengthened Pacific worker circulation, increased trade winds. And these are in agreement, for example, with the climate report from CCRS that was presented earlier this year. Wetter and warmer Southeast Asia as well, in agreement with these projections that were earlier done. And I hope to share more soon. So we recently submitted this, and it's currently under review in Nature Geoscience. So the next question here, right? So I was interested in understanding the evolution of this climate dynamics over the years. We did that. Now, what is the intersection with weather extremes in the region? Well, they seem to aggravate weather extremes, these emerging patterns. So in particular, we seem to see increased frequency of heat waves and increased frequency of extreme rainfall with some distinct spatial distribution for both. More blue and more red means more extremes. And they seem only partly explained by ENSO-driven variability. This is perhaps one of the first studies that is able to disentangle global warming trends from variabilities in the tropics, okay? And we can ask an additional question. What are the dynamical precursors of these extreme events? In other words, what happens the days before an extreme event strikes? To take a human view on this, we can again look at these composite anomalies maps. We want to identify coherent patterns in some variables that are systematically there before heat waves. Here we focus on Indochina and heat waves. We focus on a very narrow region and heat waves because obviously dynamical pathways for different events in different regions are different. So we focus on one, Indochina, okay? And if we look at these anomalies, we identify indeed some coherent patterns. In temperature, we find, and sea level pressure, we find some coherent patterns in South China preceding these heat waves, and some anomalies in water vapor in India. Precipitation also we see something, but it's not as distinct as these others. Okay, so this is somehow what I would define as a human view. Now, and these are things that we fully understand. So we use dynamical system theory. This is something we understand. We have tools that we understand, developed over centuries. What about a machine view of the same topic? And this brings me to my third point here. We are going to focus on heat waves and extreme rainfall in Indochina. For the reason I mentioned earlier, dynamical pathways are different for different extreme events and regions. And we take a look at the precursors to those extreme events, okay? So what do we do here? Well, we took the 5 days prior to an extreme event, as I did with my human view of this, before the onset days. We use 4 input variables in this case with daily data from 1940 to today, in fact, to 2022. And we are exploring different configuration variables in collaboration with Juntao Yang and Jeff Eddy from NVIDIA here. What do we have then in terms of heat waves and extreme precipitation? So we want to classify whether this day, onset day, based on these 5 previous days, is either an event, a heat wave, or a no event. Same thing for extreme rainfall, okay? So that is the setup we use. The task is actually not an image classification task. It's a time series classification task. We use the underlying time series to do this. And we use, in this case, a transformer neural network. We tried different other configurations of neural nets, but in this case, we use a transformer. And the results look like this for both heat waves and extreme rainfall. So heat waves, we get an accuracy of 88% with 76% heat waves capture, 91% for rainfall with almost 86% of extreme rainfall capture. Now, these are okay results. We are now working to improve them, including additional variables and so on. But this was not my original question. I want to take a machine view. This doesn't give me really a machine view. It gives me just a prediction of what the machine think about the next day. How do I take a machine view? Or can we even take a machine view and connect it to human knowledge? Well, in my view, we can through some post-hoc interpretability methods, something that we've been working over the past few years. What is at glance a post-hoc interpretability method? Well, here I take the example of patient's ECG, and the machine is tasked to classify what disease the patient has, okay? So let's assume that the machine says, well, based on this time series, I think that the patient has disease A, okay? Well, what did the neural network use to make that prediction? So this is the key question, right? So these post-hoc interpretability methods, they provide these relevance maps, where the red portion here of the data is what the machine used to make the classification of disease A. So we have an understanding of what data the machine used, okay? Now, this comes with a caveat. So if you use different post-hoc interpretability methods, you get widely different relevance maps, okay? So and this is what we've been working on this Nature Machine Intelligence paper we published last year. So we developed a framework that is able to measure the accuracy of the relevance maps that are produced by these post-hoc interpretability methods. And we are still working on it. We're going to submit to ICML further work on this and a few other things. So we are now somehow confident that what we get out of these neural networks is what the neural network used to make its prediction. Well, so then we can apply this framework to the weather extremes that I just mentioned. I'm going just to focus on heat waves for the sake of time here, but we also applied it to extreme rainfall, and we're applying it to other stuff. So what is the machine view on this? So these are the relevance maps I just showed for the ECG. Can we find some coherent patterns that the machine is using here or some specific region? Well, it seems so. So we see something in South China in terms of temperature, something in sea level pressure, still South China, and something here in Western India, right? What was the human view? So coherent anomalies in South China, sea level pressure, temperature, and something happening in Western India, among other things. So there seems to be some overlap between machine view and human view. We can go further, and we can ask ourselves, well, what is the domain knowledge, human domain knowledge about this topic, Indochina heat waves. So, and you can do that task two ways. Either you search on Google Scholar or you ask a ChatGPT. So here we went on Google Scholar and we find this paper, Climate Dynamics, 2018. And not surprisingly, they point out that precursors to these Indochina heat waves are temperature anomalies in South China. It is what we identify with the machine and what we identified with our composite anomalies. Interestingly, however, the machine also looks at some water vapor in Western India that is not a dynamical precursor or dynamical pathway that is well known in the domain-specific literature and could open some modeling opportunities. So, and here is my next question. Can we increase this somehow human knowledge via explainable AI? So I want to step back a few centuries here to Galileo Galilei, here the famous experiments throwing balls down the Pisa Tower. So how do we learn as humans? We tend to learn through observations, among other things. So Galileo Galilei observed these balls landing at the same time, and after a few more years, and other scientists working on the topic and adding additional observations on this, we know the force between two objects. We, in other words, generalize observations, and we were able to come up with principles, equations, right? That is how somehow tend to work in the scientific field. What's about machine learning? Well, machine learning, at least the supervised learning, we have some data and outputs, labels, and we try to somehow build a model, a program, and we test this on unseen data, and if the model generalizes well, perhaps it discovers some principles, right? And if these principles, right, are better than the one we know for that task, or in other words, the machine is better at the task than us, for example, it's better at playing chess, we might want to know what these principles are. And currently, this is a very unexplored field. So here, what I suggest is that we have a very good opportunity to apply some of these explainable AI tools to scientific applications in general. And in the context of other applications, I pull up again the same example as before, where, for example, we can discover these new, perhaps, dynamical pathways that might be there passing through domain scientists and giving this information. Is this a foolish avenue that I'm suggesting here? Well, I really like this editorial from the New York Times by Strogatz, a famous mathematician from Cornell. So here is an IBM employee against Garry Kasparov, a human world champion in chess. The IBM employee is moving the pieces for Deep Blue, a chess machine, right? And the editorial is about 20 years later. So IBM Deep Blue beat Garry Kasparov in 1997, and DeepMind's AlphaZero beat Stockfish in 2017. This editorial is about this achievement. And Garry Kasparov, about the victory of AlphaZero, commented, well, it seems that AlphaZero discovered the principles of chess. And Strogatz goes forward and says, well, it discovered some important principles about chess, but can share that understanding with us, okay? So this is a lack of interpretability or understanding. So I'm not suggesting to learn from machines, am I? Perhaps I am. In fact, I don't think it's a completely foolish aspect here. There was a recent paper, PNAS, reported by Scientific American in 2023, and they show that human Go players are now improving their skills at Go, looking at patterns identified by AlphaGo, which is an AI machine playing Go. So perhaps it's not a completely foolish route to take. So the take-home message really for today, in my view, is to and from AI, or explainable AI. So when we can infuse knowledge in AI systems, I think this is an important skill to constrain to physical solutions, what is being done in physics-informed AI, physics-informed neural network. But I think we have a very good opportunity here to perhaps try to fill some knowledge gaps with explainable AI. Oops. So I want really to conclude with this slide about Richardson. So Richardson, that I introduced earlier, in 1950 actually witnessed the first computer simulation of the weather, stating that it was an enormous scientific advance. And ENIAC predicted the weather for the next 24 hours in 24 hours. Now, since then, we did a lot of progress, obviously, and I think now AI tool and possibly explainable AI tools are a very good opportunity to further advance the field. So to conclude, I really want to thank my PhD students here, part of my lab, MathEXLab, and the sponsoring agency, Asst, Ministry of Education, and NUS. And I should point out that outside we have a poster looking at public perception of weather extreme climate resilience done with NLP. So it's part of also this work with Prof. Eric Cambria and Dr. Rui Mao from NTU. And we are also applying some of these techniques on a new corporate venture here. Thank you.